Hi everyone, welcome to lecture number 6 of Data Science and Artificial Intelligence Complete GATE course. And we are discussing probability right now. We've already seen what independent events are, conditional probability is, and we have seen a few questions on that. In this lecture, we will see very important key terms. Okay, so the questions in GATE, generally what I've seen in statistics, probability is already there in almost like many of the GATE papers, right? Statistics is one of them, and GATE computer science already has been asking questions on it from past 20 years, and data science is being introduced recently. But what we have seen is questions generally will be not directly from marginal or joint probability. You won't see, but these are key terms. Okay, you need to know what marginal probability means, what total probability is, what joint distribution is, what prior is, posterior is, and when you combine all these 10 strings together, like Bayes theorem, conditional probability, anything, when you combine all of them together, the question can be from the entire concept. Okay, so it's very important to practice. So after doing all the sessions, you will do a lot of practice questions, and questions can be mix of multiple concepts that you have seen. Cool. So let's discuss marginal and joint probability, what it means. We already know what conditional probability is, but again I will explain it because as a part of this video we have conditional probability is very closely related to marginal and joint probability. So it's very easy for you to confuse between conditional probability and marginal probability. Cool. So we already know what a probability of a single random variable looks like, right? We just say ki there is a sample space, which is the universe, and there is an event which can happen or not happen, and we have a probability associated with that event. Probability of that event E, P of E, or probability of X being A or something like that, right? So this is a single event, and a single event has a single random variable associated with it. So the probability of a specific event A for a random variable X is denoted like P of X equal to A. So for example, let's say you're throwing a die, and the random variable is what is the number that you're getting. So X can be 1, 2, 3, 4, 5, 6, right? There are 6 possible values X can take, and we say that probability of X being 2, we know that it is 1 by 6. We can say that probability of X being less than 3. So if you want X to be less than 3, X can be either 1 or 2. So the probability is 2 by 6. So this is a random variable for a single event, right? So the probability of a random variable taking any value depends on the event, what you're trying to say, okay? So the probability of an event A is denoted by P of A. This we have already seen. For a single random variable, we have seen everything. So the probability is calculated as the number of desired outcomes divided by the total possible outcomes which are possible, and that's how we define it. For example, here the total possible outcomes were 6, and we wanted just the value to be 2. So 1 by 6 was the probability. Total number of desired outcomes upon total number of possible outcomes. And there are certain axioms for probability of one variable, one random variable, or a single event. We know that sum of probabilities of all possible outcomes is always 1, and probability of an impossible outcome is 0. Probability of a certain outcome, which is always likely, it is guaranteed to happen, is 1. And probability of not happening of an event is 1 minus probability of happening of an event, okay? And it is also called the complement of an event. These things are all we have seen in the past few lectures, and they are related to a single event, okay? Or a single random variable. Now what can happen is, generally in machine learning specifically, in ML problems, you won't be working with a single random variable. I told you previously, we had seen an example. For example, you want to see the correlation between 2 data sets. Is a pen really bought with a pencil? Okay, so generally all stationery items in a grocery store are put together. Okay, and similarly all grocery items are put together. So what happens is people are have a tendency to buy these things together. So you want to see correlation, right? Here we have multiple events. Generally in ML, almost all problems will have multiple random variables associated with it. You are not trying to maximize or minimize a certain single event. You will have 3 or 4 different random variables and a big data set, and then you want to analyze patterns on that. So in ML, we are likely to work with many random variables. We assume that 2 variables are related or dependent in some way. And also we have seen, see, we have worked on 2 or 3 events together as well. I told you ki 2 events are independent. I told you the definition of that. 2 events are mutually exclusive. They are exclusive if their probability of intersection is 0. They cannot happen together. And what is independent events? A and B are independent if happening of one event doesn't influence the happening of other. Okay, that is different from mutually exclusive. So probability of A given B has happened is equal to P of A, right? So these are independent events. So we have seen multiple events together, but now we will see the association of multiple events and a joint probability table. That's the difference, okay? So we assume that 2 variables are related or dependent in some way. So the random variables are from the same event. So for example, see, like throwing a die. So let's say your experiment. There are various terms in probability, okay? It gets confusing sometimes, but when you solve too many problems, this will be easy. So let's say the experiment is throwing a die. Okay, we know what is the sample space. We have 6 possible values. Let's say the event A is getting a prime number. So the event A is defined as 2, 3 and 5. Let's say the event B is getting an odd number. It's a different event, 1, 3 and 5. Okay, so these are events. These are not random variables right now. Now what will be a random variable? Let's say now I define a couple of random variables. Ki X is a random variable and Y is a random variable. Let's say X is the number that you get when you roll a dice for the first time. You roll it for the first time. Okay. So basically you're rolling the same die twice. First like 1 and then twice. And Y is the number that you're getting when you roll it for the second time. Okay. This is a random variable now. So now these are 2 events, 2 separate experiments that you're doing in some way. They might or might not be independent from each other. Right now if you're throwing 2 dice, the number which are appearing are independent from each other. It doesn't matter what you got in the first attempt, right? So they're independent from each other. So they might or might not be dependent on each other. But this is what like random variable looks like. So these random variables can be dependent or can be independent from each other. So now we have various probabilities associated with it. For example, like what is the probability? What is the probability that the random variable X is greater than the random variable Y? This is a problem now. You have to get a larger number on the first roll than the second roll. Okay. So this is the difference between random variable and an event happening. And the concept of joint marginal conditional probability work on random variables like differently. So we will explain, like I'll explain like what a joint probability distribution is and how random variables, like different random variables, get associated to each other. So there are 3 main types of probability we consider when we talk about multiple random variables. We talk about joint probability, we talk about marginal probability, and we talk about conditional probability. So what is joint probability? It is the probability of events A and B both happening. So for example, here in this example, probability, let's say I tell you, let's say the event A, forget about these events A and B. I'm creating new events A and B based on the random variables X and Y. Let's say the event A is getting an odd number on the first die, odd number on the first die. It means that X has to be equal to 1, 3 or 5. And let's say the event B is getting a prime number on the second die. Okay, we know that these events are independent because like throwing a die, the 2 events are always independent of each other. So these 2 events will be independent of each other. That's okay. They might or might not be independent. But what is the joint probability? Joint probability will be probability of A is happening and B is also happening. A and B. So we write it like this. So basically it is like probability of X being inside odd, which means 1, 3 and 5, and y is prime, which means y has to be 2, 3 or 5. Okay, this is joint probability. Probability of happening of both the events. What is marginal probability? Probability of only, so we only consider one random variable in marginal probability. It doesn't matter what the other what the other random variable is doing. Okay, what the value the other random variable is getting, it doesn't matter. Combining all the values which other random variable can get, what is the overall probability of happening of one random variable? That's all. That's marginal probability. Okay, with example it will be much more clear. In the next slide we will see an example. And conditional probability we already know. Okay, what is the probability of event A given B has already happened? So given that the random variable y was this, like let's say given that the random variable y is 3. Now what is the probability that the random variable x is 2? So if these two random variables are independent of each other, then it doesn't matter what the value of y is. Okay, probability of x will remain same. But if they are dependent, it might change. So this is what conditional probability is. So now let's see an example. With this example, everything will be very clear. So let's consider two random variables x and y and their joint probability table. This is called a joint probability table. Okay, what it means? Joint probability table will always contain joint probability values. So which means probability of x being 1 and y being heads is 1 by 12. Probability of x being 2 and y being tails is 1 by 12. So this is what joint probability table means. Basically writing all possible joint probability values for all random variables. Okay, so it will have all the values possible. So here we have two random variables x and y. So the random variables are, what we are doing here, so the joint probability table shows the probability of each combination of values for x and y. And the random variables are, x is the result of rolling a fair 6-sided die. So you are rolling a 6-sided die and the whatever value you are getting, that is x. Okay, so this is an experiment. You are rolling a 6-sided die and whatever value you are getting is the random variable x. We know that the possible values are 1, 2, 3, 4, 5 and 6. Similarly, random variable y is like this. It is the outcome of flipping a fair coin. So now you flip a fair coin. It's like unrelated to what you were doing before. Okay, and here we know that the possible values are only heads and tails. Right? So now what happens? We know that probability of getting a 1 on the fair die and getting a heads on on flipping the fair coin will be what? So it is like probability of x being 1 and y being heads. It is the intersection, and means intersection, right? Now it is very obvious in this example that x and y are independent of each other, right? Which means that it doesn't matter what you're getting on the flipping of coin. It doesn't matter what you're getting in the flipping of coin. The value of die doesn't matter. So that's why this will be probability of x equal to 1 times probability of y being heads. Okay, this we already know from the definition of independent events, which means what is the probability of x being 1? It is 1 by 6. And what is the probability of y being heads? It is 1 by 2. So it is 1 by 12. And similarly for any possible combination, the value will be always 1 by 12. So basically what we did, we created probability of every joint possibility, probability of events A and B. So we basically have written down in this table all possible outcomes for both the variables, and observe that at least one of them will always happen. So that's why the sum of all this probability will always be equal to 1 in a joint probability table. If you are writing all possible random variables and all possible joint values, then the sum of all these values will always be equal to 1. So here it is the case. So this is called the joint probability table. Cool. Now we will see all the different terms. So the first term is joint probability. Obviously it is very simple. Again, if joint probability table is given, calculating joint probability is very easy because this table contains joint probabilities, right? So for example here, probability of x being 3 and y being heads. This is called joint probability of event A and B. Here A is getting a 3 on the die and event B is getting a heads on the fair coin. Okay. So here if you want to calculate the joint probability, just look at the table. X being 3 and y being heads. It is 1 by 12. Okay. So sometimes what can happen here, the problem was much simpler. The dice was also fair and the coin was also fair. But sometimes the problem might be like complicated, and these events can be dependent or dependent on each other as well. Here they were independent, so that's why it was easy. Cool. So calculating joint probability is easy, right? Just see the table and just mark the values and you will get the answer. Now coming to marginal probability. So marginal probability is the probability of a single event. Marginal probability is the probability of a single event without considering the occurrence of any other events. So what happens is, always we talk about these things. We talk about these things only when we have multiple random variables, that we have already seen, right? We will have 2 or 3 random variables. So it doesn't matter what the value of other random variable was, you sum up all possible such values. Now you want to calculate the probability of only one random variable. For example, here, probability of x being 3. This is called marginal probability because we are not giving you the value of y. We are not giving you the value of y. We only worry about the value of x. That's how it is called marginal probability. So how to calculate that? Just go to the x equal to 3 row and sum all these values. It doesn't matter what y is. Y can be heads, tails. You can have 3-4 more values. It doesn't matter. If you want to calculate marginal probability, just sum the entire row. 1 by 12 plus 1 by 12. It will be 1 by 6. And we already knew the probability of x being 3 will be 1 by 6, right? Because it doesn't matter what we get on the like on the coin. Probability of getting a 3 on die is 1 by 6. So that's how you calculate marginal probability. You can calculate one more. So what is the probability of y being tails? If you have to calculate for other random variable, that is also possible. It doesn't matter what x is. So you sum all these values. You sum all these values and you'll get the probability of y being tails. So you sum all this, you'll get 1 by 2. Right? Now coming to conditional probability. So conditional probability we already know, right? It is probability of happening of one event given that other event has already happened. See, that's the biggest mistake that I have seen like a lot of students make. Total probability table, joint probability table doesn't contain the information of conditional probabilities. You can calculate them using that table, but directly here the values don't represent conditional probability. This value 1 by 12 here is not the conditional probability of x on y. It is the joint probability. It is probability of x being 3 and y being heads. It is not probability of x being 3 given y equal to heads. Okay, this is different, this is different. And means intersection. This is conditional probability. Okay, so the joint probability table contains joint probabilities, not conditional probabilities. Conditional probabilities you will have to calculate. In this example, this value will also be equal to this value. In this example only, this value is equal to this value because x and y are independent events. They are independent random variables. It doesn't matter what happens to y, like the probability of x remains same. But in most of the example, this will not be the case. Then you will have to calculate the conditional probability, right? So what is conditional probability? Let's say I want to calculate probability. So let's say I want to calculate probability of, here we have an example. Let's say I want to calculate probability of y being tails given x is equal to 4. Okay. What is the probability of y being tails given x is equal to 4? So we know that it will be by formula. Just go by formula. What is the conditional probability formula? We know the probability of A given B has already happened is probability of A intersection B upon P of B. Right? This we already know. So it will be probability of y being tails and x being 4 upon probability of x being 4. So the conditional probability is equal to the joint probability upon marginal probability. See, now we are getting all the terms, right? This is joint probability. This is marginal probability. So how to calculate the probability of y being tails and x being 4? Y being tails and x is equal to 4. So it is 1 by 12. And what is the probability of x is equal to 4? X is equal to 4. How to calculate the marginal probability? Sum all the values. 1 by 12 plus 1 by 12. It is 1 by 6. So it is 1 by 2. So what is the probability of y is tails given x is already 4? It is 1 by 2 only. In this case, see, it is not equal to the joint probability here. It is not equal to the joint probability of y equal to tail and x equal to 4. That was 1 by 12. But here we are getting 1 by 2. Right? So marginal probability, joint probability is different from conditional probability. And also here, only in this example, this is also equal to probability of y being tails. Right? Why? Because these two events were independent from each other. So when A and B are independent, we know that P of A by B is equal to P of A. Here it is the case, that's why they are independent from each other. Okay, next, so I will take an example in which the events are not independent also. Okay, there it will be more clear. So I hope you got the concept: joint probability, marginal probability, and conditional probability. Now let's see like another complicated example. Here it is not given that x and y are independent or not. Okay, it is not given x and y are independent or not. We will calculate it. Okay, so you are given two random variables x and y, and we are given the joint probability distribution. It is also called the joint probability mass function. It is same as probability distribution. Okay, later when we see random variables in detail, we will have like in probability, this is basic probability. Okay, we will have random variables in detail. There we will see what probability mass function and cumulative distribution, all these are. We have in what discrete random variables are, what continuous random variables are. For now, just assume that joint PMF is nothing but joint probability distribution. Okay, so basically all these values denote the joint probability of x being 2 and y being 4. It is 1 by 12. Okay, so this is the joint probability distribution given. You can see that the sum of all these values will be 1. Okay, and so what is the joint probability of, let's say, x being 2 and y being 4? It is 1 by 12. This value. Okay, so this is called joint probability. Now you want to find, so the question is, you want to find probability of x being less than equal to 2 and y being less than equal to 4. That's the question asking. So basically it's not just a single joint probability. Here, so x can be less than equal to 2 and y can be less than equal to 4. So there are multiple such possible options. So basically x can be 1. See, the possible values of random variable x are given to be 1, 2 and 3, and for y they are given to be 2, 4 and 5. That is okay. So what they are saying is x has to be less than equal to 2. So x can be either 1 or 2, and y has to be less than equal to 4. So it can be either 2 or 4. So what are the possible combinations for x and y which will obey this probability? So the possible options are x being 1 and y being 2, or x can be 2 and y can be 2, x can be 1, y can be 4, and x can be 2 and y can be 4. These four combinations satisfy the condition given. So basically we have to sum all the probabilities, these four joint probabilities basically. So these are the four probabilities. In these four joint probabilities, the condition is satisfied, which means x is also less than equal to 2 and y is also less than equal to 4. So we just sum all these four values. So we will get 1 by 12 plus 1 by 24 plus 1 by 6 plus 1 by 12. So the denominator becomes 24. 2 plus 1 plus 4 plus 2, 9 by 24, which is 3 by 8. Okay, so this is the probability of x being less than equal to 2 and y being less than equal to 4. Cool. Now the next question is, find the marginal probability distribution of x and y. So basically they want to find the, like here in this question we want to find all the marginal probabilities of x and y. Basically probability of x being 1. This is the marginal probability of x being 1. Then we have marginal probability of x being 2, x being 3. And similarly marginal probability of y being 2, y being 4 and y being 5. The question is asking you to calculate all of them. I will just do 1 or 2 and the rest you can do it. Okay. So what is the marginal probability of x being 1? You just sum this entire row. Okay. So it will be 1 by 12 plus 1 by 24 plus 1 by 24. So it will be 2, 3, 4, 4 by 24, which is 1 by 6. Very easy, right? Marginal probability. What is the probability of x being 1? You just sum this, this and this, because y can be anything. It can be 2, 4 or 5. You're summing all these up. Similarly, like let's calculate one more. What is the marginal probability of y being 4? So you want y to be 4, so you just sum this entire column. So it is 1 by 24 plus 1 by 12 plus 1 by 8. So it is, denominator will be 24, 1 plus 2 plus 3, 6. So it is 1 by 4. Okay, you sum all these values. So similarly, you can calculate all other marginal probabilities as well. Okay, I just calculated 2. So here is the answer. You can take a note. So we calculated probability of x being 1 to be 1 by 6, which is correct. And we calculated probability of y being 4 to be 1 by 4, which is correct. Okay. Similarly, you can calculate the other marginal probabilities as well. Cool. Now let's look at the next question. Here you need to find the probability of y being 2 given x is 1. Again, most people make a mistake. They will just directly say it is 1 by 12. No. What is 1 by 12? 1 by 12 is the joint probability. Probability of x being 1 and y being 2 is 1 by 12. Here we have to calculate something else. Here we have to calculate probability of y being 2 given x is 1. Interesting problem, right? Like this is conditional probability. So just go with the formula. Okay, it's very simple. Like we know how to solve it. Nothing to worry about. If you read the statement, calculate carefully, it will be very simple. So what is this? What is P of A given B? It is P of A and B upon P of B, which means probability of y equal to 2 and x equal to 1 upon probability of x equal to 1. I told you conditional probability is nothing. It is joint probability upon marginal probability. That's what you're getting here. What is the probability of y being 2 and x equal to 1? This is 1 by 12. And what is the probability of x equal to 1? You just sum the first row. We already did it, right? It was 1 by 6. You just sum the first row. So this is what the conditional probability of y being 2 given x is 1. See, this is interesting problem, right? Given that x is 1, so only these 3 cases can happen. Now your sample space reduced. Your sample space is only these 3 values. Among these 3 values, only this was interesting for you. That's why it was 1 by 12 upon 1 by 12 plus 1 by 24 plus 1 by 24. Okay, it's very logical. So what is this? This will be 6, 12, 1 by 2. Cool. So this is the conditional probability of y being 2 given x is 1. 1 by 2. See, now can you calculate what is probability of y being 2? That's all. I want to see these 2 events are independent or not. So I will just calculate probability of y being 2. If that is also 1 by 2, then these 2 events will be independent, right? What is the probability of y being 2? You just sum the first column. So it is 1 by 12 plus 1 by 6 plus 1 by 4. So the denominator will be 12. 1 plus 2 plus 3. So it is 1 by 2. It is correct. Probability of y equal to 2 given x equal to 1 is equal to probability of y equal to 2. Which means that these 2 events are independent from each other. Only we can say that. We cannot say that the random variables x and y are independent. For random variables x and y to be independent, all possible such combinations should be true. Basically, like none of the variables should be dependent on each other. Right now, we only know that probability of y being 2 is independent from probability of x being 1. It can be possible that probability of y being 2 is dependent on x being 2. Okay, it is only independent of x being 1. But yeah, that is correct. Okay, so the probability right now which we wanted to calculate was 1 by 2, and we also proved that these 2 events are independent at least. Okay, yep. Now the real question is, are x and y independent? Like, so are the random variables independent? For random variables x and y to be independent, what should happen? all such combinations should be independent of each other. So like y being 2 should be independent of x being 1. Y being 2 should be independent of x being 2, and so on. Basically check everything. So we can do it quickly. So we already checked y being 2 independent of x being 1. Right. See, I will tell you a very quick way to do this. You already calculated the marginal probabilities, right? I will do that again here. Let me just copy it from here. 1 by 6, 3 by 8, 11 by 24. So for x being, so the marginal probability of x is 1 by 6, 3 by 8 and 11 by 24. This is basically the sum of first row, second row and third row. I have written the sum here. So this is the marginal probability of x, and here I am writing the marginal probability of y. So marginal probability of y we calculated to be 1 by 2, 1 by 4 and 1 by 4. This is the sum of columns. So I told you that independent events have one more property. One of them is this. There was another formula, right? When we rearrange it, we get probability of A intersection B is probability of A into probability of B. Right? This is the independence theorem, right? Like two independent events are independent if probability of their intersection is product of their individual probabilities. You can get this from this. We already did that. So basically what you need to check is this probability should be product of this and this. That's all, right? That's much easier to do, right? Instead of calculating the conditional probability every time, checking this is simpler. See, 1 by 12 is 1 by 6 into 1 by 2, correct? Which means that y equal to 2 is independent of x equal to 1. This is independent. Just check this product. Is 1 by 6 equal to 3 by 8 into 1 by 2? No. We found the example in just the second case, okay? What could have been the blunder? In this question, you might have made a blunder. You just check the first value. First value is correct, right? The first value here, this is the product of 1 by 6 and 1 by 2. So it makes y equal to 2 independent of x equal to 1. But it doesn't make y independent of x completely. For y and x to be independent, all these values should be product of these two values. But here, y equal to 2 is not independent of x equal to 2. Okay, this product is actually 3 by 16, which is not 1 by 6. Which means that I don't need to check all other values. I found one value, which means that random variables x and y are not independent. They are dependent. Only few combinations are independent of each other, but not all. So that's why x and y are not independent. Okay. Cool. And similarly, like in this example, they were independent. The entire events were independent. Why? So here also, if we do marginal probability for x equal to 1, this will be 1 by 6. All of them will be 1 by 6. Or here the marginal probability of heads and tails will be 1 by 2 and 1 by 2. And all the values are product of these two values. You can check, right? Very simple. So here all events, all possible combinations are independent of each other. That's why the random variables are independent of each other. But in this case, they are not. Cool. So yeah, we will discuss some more problems on this, and we will see more like interesting applications of these topics that you have seen. So just remember the terms, okay? Marginal probability, conditional probability and joint probability. We will use these terms in the next two lectures, which will be on total probability and Bayes theorem. Very important coming to probability. So see you next time. Thanks.